College, Puri in 2005, MSc in Mathematics from Utkal University in 2007, and MPhil in Mathematics from Sambalpur University in 2010. Dr. Rout has 19 publications so far in reputed journals, and he has submitted 5 preprints for book publications. Dr. Rout has participated and delivered talks in numerous conferences and workshops. He has gone on post-PhD academic visits to ISI Delhi, NIT Rourkela, the University of Sopron, and University of Debrecen in Hungary, and HRI Allahabad. Dr. Rout was awarded the National Rural Talent Scholarship by Government of Odisha in 1997 to 2001. Dr. Rout had qualified GATE in 2010 and CSIR NET in 2011. He was awarded the NBHM Postdoc Fellow in 2015 and Professor A.K. Agarwal Award for Best Publication by the Indian Mathematical Society in 2017. Now I welcome Dr. Rout to deliver his talk. Thank you, sir.
You are not audible, sir.
Okay, so thanks, Sunita Chance, for these nice words about me, and I also thank Dr. Abhijit Sutrodhar, the co-convener of this weekly academic lecture series. So today I would like to discuss about these S units and perfect powers in linear recurrent sequences. So basically, this talk is a review talk. There is no proof at all, and I will use my tablet to I will use my tablet to write all the. I will not do any presentation here. Just I will like the Blackboard presentation. I will do my presentation here. So let me share my screen first. So, is there an issue? I am unable to share this screen.
You have not shared.
So no. Actually, I am. There is something. It is Google Chrome might not have screen recording mission on your screen.
Are you using Wacom or what? Are you using Wacom?
Yes, Wacom. Yes.
Then present the screen. Open the Wacom. Present the screen.
Present. Yes. Okay, yes. Just a minute.
Open the Wacom.
Oh yes, I opened the Wacom.
Now you present the screen. It is not showing that you are presenting the screen. It is not showing that.
Actually, the issue is it is not coming actually. Your entire screen I'm doing, then Chrome wants to share the consoles your screen with you.
Look at the bottom line. There will be present the screen.
Yes,
There will be an arrow kind of thing you see.
Yes, that I've seen, but it's not.
Dr. Abhijit, if you can help.
Yes, sir. Dr. Rout, you can click on the
yes, I'm doing that.
dots.
Just a minute.
Yeah.
Sudhanshu sir, if you are using Wacom for the first time, then you have to install
No,
drivers of.
no, I am not using. I'm taking classes on this board, but today I'm using this Google Chrome actually. I'm generally I'm using Safari, but that is the issue. I'm unable to do all this.
Okay, okay, okay.
So there is a different browser. That's problem. अरे ये काजी शेयर भी होने कौन ये काजी
Sir, share option is not coming, na?
Dr. Rout, you can use your old browser then if it is not working in Google Chrome.
If share option is not coming, then that monitor, whatever it is visible, you just click there and then share option will come.
Dr. Rout, please unmute your Google Meet microphone so that we can communicate to you. Yeah.
sorry for the
So are you
Okay.
trying from old
You
browser
can
or
So that old browser, I told that there is some issue in old browser. That is, this Google Meet is not responding in that browser. Right there.
so you can use your old browser then.
That I'm saying, na, that old browser is not responding to Google Meet today.
Okay.
Also, speaker can speak something about his topic.
No, just a minute, because many all the things depends upon this writing actually. So let me try for a few minutes.
No, just for a discussion, formal discussion with few minutes, not full lecture. He cannot speak, but at least some idea he can speak.
Let me try for a few minutes, then.
Yeah, sure.
Otherwise, doctor, you can use your mobile. In mobile, there are so many options are there to write in a pad. So it is also applicable, no problem.
In mobile, you can write.
But if he has not used first time, he can use. This will be difficult.
No, I'm telling about mobile. You can use mobile screen to write something.
Even if in mobile also, if he has not used mobile prior to this, then it is very difficult to use mobile also. This happens kabhi. Dr. Abhijit, you can make a video call through WhatsApp and can see these things.
what's video call through WhatsApp?
Then you can see the things. Where is the problem?
Where is the speaker? The speaker has left.
This happens sometimes, isn't it? Because he was using a different browser, now he is opening Google Meet in that browser. It may not be compatible also.
Yes.
Dr. Priyanka, Dr. Priyanka, you there?
Yes, sir, I'm here.
Okay. Okay. Whether Soumya has called you?
Dr. Soumya, no, sir.
No, no, not Dr. Soumya. Soumya, student.
Yeah, Soumya Ranjan sir, yeah, he called me.
Okay. Okay.
Yeah. Actually, he is at home right now, so I asked him to provide
Can
me
you
his.
can you see my screen now?
Okay. Okay. Carry on,
Yes,
Professor.
yes.
Is it audible and is it visible to my screen?
Yes,
Yes,
yes.
yes, yes.
Okay, thank God. So it is too late and okay.
Thank you for this effort.
Okay, sorry for this disturbance. Actually, these technical gadgets I'm not so comfortable and okay.
It's all
So
right. All right.
mm, so let me
Please go
start
ahead.
from the very. So today's topic is on this recurrent sequence. So let me start with a very well-known sequence that is called Fibonacci sequence. So let me directly go to the definition and I will discuss some basic properties. Then we'll see some important results proved in last century on this particular recurrent sequences. Okay. So so I'm denoting this Fn. Can you see my screen or not?
Yes,
Hello.
sir.
Yes. Yes.
So this Fn is my nth term of Fibonacci sequence. I will define what is this Fibonacci sequence. Okay. So this is the nth term, and Fibonacci sequence is generally defined by a recurrence relation, and that recurrence relation is of this form. This n plus 1th term is given by the sum of two previous terms, fn plus fn minus 1, and with two initial values, that is f of f0 equal to 0 and f1 equals to 1. So if I start with this 0 1, and if I want to find the second term, that is f2, then I have to add f0 plus f1, then I can able to find f2 equal to, so from this I can write f2 equal to f0 plus f1 equal to 0 plus 1 equal to 1. Similarly, if I want to find f3, then I have to write f3 equal to f2 plus f1, that is equal to 1 plus 1 equal to 2. So it's similar, I can continue. So this you can write n is bigger than equals to 1. Okay. So in this way, we can find all the terms of this recurrent sequence. That is called every term that nth. Also, we can write. Suppose I want to find the 10th Fibonacci number in this sequence, then I have to find the first 9 terms. Then only I can able to find the 10th term. Is it clear? The thing is that, so if somebody will ask me how to find the 1000th term of this sequence, so what shall I do? So in this process, if I will try to find the 1000th term, then I have to find the first 999 terms. So that is a very tedious job. So now the question is how to find a closed formula. So this is a formula we can able to find the next term of a recurrence sequence using this recurrence relation. But this is not quite easy to directly find any other terms of a sequence. For this, we have to find the previous all the terms. So for that, we have to generate a new formula so that we can directly compute any terms on this sequence. So for this, so let us recall what is a generating function. From that, we can able to produce a new formula for this nth term of a recurrent sequence. Okay. So let n be any sequence. N is bigger than equals to 1. This is any sequence. Be a sequence of suppose real numbers. Or you can take integers also. So real numbers. The formal power series. The formal power series fx equals to summation n x to the power n, where n is bigger than equals to 0. This is called the generating function of this sequence again. So that means if I know this capital F of x, then I can able to find all the terms of this recurrent sequence. This is called, that's why it is called generating function of the sequence AN. Okay. So when I'll start with n equal to 0, this is a0 plus a1 into x plus a2 into x square, like this, it will continue like this. Then you can see the coefficient of x to the power n is the nth term of the recurrent sequence, this nth term of the sequence an. So using this generating function, we can able to, so let us, what I will do, we will try to find a generating function for our sequence. Then only we can able to get a closed formula. So to find generating function, we'll use this recurrence relation, that is fn equal to fn minus 1 plus fn minus 2. So what I will do, so if you recall, this is n is bigger than or equal to 2 and f0 equal to 0 and f1 equals to 1. So let us write like this: f of x equal to summation n equal to 0 to infinity fn x to the power n. So this fn is the nth term of this recurrent sequence. So since f0 equal to 0, I can write this summation equal to n equal to, from not from 0 but from n equal to 1 fn x to the power n, because f0 equal to 0. Okay. So that's why. So now if I put n equals to 1, the first term is f1 is 1, so I can get x because f1 is 1 into x, plus the second term is, so from second term onwards, let me write like this: n equal to 2 to infinity fn x to the power n. Okay. So again, I can use, because this formula is valid for n is bigger than or equal to 2. So now I can write this expression as summation n is equals to 2 to infinity. This is fn minus 1 plus fn minus 2 into x to the power n. Okay. So this is once this is known, then I can remove this bracket. So this is x plus summation n equal to 2 to infinity fn minus 1 x to the power n plus summation n equals to 2 to infinity fn minus 2 into x to the power n. Okay. So now what I will do, I will write, so we'll do something here. So some n equal to 2 to infinity fn minus 1 x to the power n. So I will write like this: I will take a common x from the x to the power n. So then it is n equal to 2 to infinity f n minus 1 x to the power n minus 1. So this sequence is something like f of x. So if you can change the parameter n to t and you can write n minus 1 equal to t, then it is something like your f of x. So this is x into f of x. Similarly, one can write n equal to 2 to infinity f n minus 2 into x to the power n as x square into f of x. So now I will plug these values x. So these values n equal to 2 to infinity fn minus 1 x to the power n, I will put that as x into f of x, and this one as x square into f of x. So if I put all these things together, so I will get this one, that is f of x equal to x plus x times f of x plus x square f of x. Okay. So if I take all these terms to the left hand side, which has f of x, then I can able to find f of x equal to x by 1 minus x square. So this is the generating function. Okay. So this is the generating function. So that means if I expand this function as a power series, I will get the coefficient f of n, and that f of n is the nth term of the Fibonacci sequence. But again, so this expansion we have to do. So for this, we have to find the roots of this polynomial 1 minus x square. So let me call these polynomials are minus alpha and minus beta, where alpha equal to 1 plus root 5 by 2 and beta equal to 1 minus root 5 by 2. They are conjugate to each other. Then I can write this f of x equal to what? So this is, I can write x by x is this something. I can able to write something like a by x minus of minus alpha plus, this is partial fraction, so x minus alpha beta. So from here one can able to find a and b using the initial values, and using this when I take the LCM, I can able to find a and b. So finally I will get a formula for this f of x. So that formula is coming like this. So if f of x equal to summation, there are some calculations, I leave it. So 1 by root 5, this is alpha to the power n minus beta to the power n into x to the power n. Okay. So if you recall, this f of x is something like summation n equal to 0 to infinity fn into x to the power n. now one can directly see that what is this Fn. So this Fn equal to this one. This one. Yes, that is the closed formula. So I can write this Fn as from this previous page, alpha to the power n minus beta to the power n by root 5, where alpha equal to 1 plus root 5 by 2 and beta equal to 1 minus root 5 by 2. So now if one try to find any terms, any nth term of a recurrence sequence, then he can use this formula. This has a name. This was first derived by the mathematician Binet. So this is called Binet's formula for the Fibonacci sequence. Okay. So now somebody, if you want to calculate 1000 term or 10,000 term, whatever, you just put the value of n and using this alpha equal to 1 plus root 5 by 2 and beta equal to 1 minus root 5 by 2, you can able to produce that term. So till now, any questions? Hello.
The question is even that 1 plus root 5 by 2 whole to the power n, how you are finding out, using Pell's equation or what?
This is the binomial expansion. You can do binomial expansion.
So that will be once again lengthy?
No.
If I take 1000, then you will see that
all these things. Okay, so so what I am trying to say is that the difference between this recurrence relation and this closed formula. So using that recurrence relation, you have to produce the previous all the terms for 1000th term. But for this closed formula, you can able to directly compute. It may take some time, but it is a closed formula. This is a direct formula. Without knowing any previous terms, we can calculate this term. Okay. Okay. So this is the closed formula for any nth term of Fibonacci sequence. Now, what is the arithmetic behind this thing? So let us, from this formula, one can quickly see that any nth term is bounded by this term. This is so I will not prove all these things. These are all proved by induction. This is alpha to the power k minus 1. This is the absolute value of Fn is bounded by this. Okay, and if you take n is bigger than or equal to 1, then always Fn is positive. So we don't need this absolute values. But sometimes n becomes z, so you can also define the negative Fibonacci sequences. So in that case, this is helpful. So this is this is bounded by this alpha to the power k minus 1, and this is also bounded below by this alpha to the power k minus 2, and alpha is this one, 1 plus root 5 by 2. So there are some other formulas, like all these formulas can be quickly proved using induction only. So this is k plus lth term of Fibonacci sequence can be derived from this fl into fk plus 1 plus f times l minus 1 into fk. So these are few formulas. There are other formulas are also there. So there is one more question I would like to ask. So if I will ask for what value of n this fn equal to 0. So question is for what n this fn equal to 0. So since this is you can see quickly from this terms of the recurrence sequence, because 0, 1, 1, 2, 3 like this. So you can say that only n equal to 0. But one can also generalize that question to this question: fn equal to c is any given number. C then, so for what value of n, fn is c. So taking the value c, that is another arithmetic question. So all these questions can be handled using this closed formula alpha to the power n minus beta to the power n by root 5. For example, if one would like to find fn equal to 0, then one would solve this equation alpha to the power n minus beta to the power n by root 5 equal to 0. That will give me this alpha to the power n equal to beta to the power n. That implies alpha by beta to the power n equal to 1. So here you can see that alpha by beta is a root of unity. So if alpha by beta is a root of unity, then that n will give you the that n is the term where fn becomes 0. But we can see that alpha by beta is not a root of unity. So this is only possible if and only if n equal to 0. Okay, so this is Fibonacci sequence, because we are just starting with a 0, 1, 1. So this is easy question for Fibonacci. But when we will go back to so we'll see in a few after 10 minutes with general sequence. Then this question is most important question. Okay, so this cannot be handled like this. Next page. Okay. Suppose now the question is, so in my abstract I have mentioned that there are many interesting different equations will arise when one study the intersection of two sequences. Suppose I will take a sequence of perfect powers, sequence of perfect squares, sequence of squares, that like I can take 1, 4, 9, 16. This is a sequence of integers which are all the terms are squares. And I am taking another sequence that is Fn, that we have already discussed. So now I will intersect these two sequences. So then I will get a Diophantine equation. So Diophantine equation is an equation in mathematics where we need or where we try to find the solution in integers actually. So that means if I would like this question, as in if I intersect this sequence of squares and sequence of Fibonacci number, then I will come up with an equation like Fn equal to x square. So what I need the answer in n and x in this positive in this set. So positive integers. So n is a natural number and x is also a natural number. So what are the so for what value of n x, so Fn is always a perfect square. So that is the intersection of Fibonacci sequence and perfect square. So this question was asked by solved by Kohn, COSN. This is in 1963. So this is a very old problem, but at that time there is no modern mathematics was developed so far. So using these elementary arguments and congruence relations, they have proved that this Fn equal to x square if and only if this. So these are the values. If you can see, so n Fn equal to 0 or 1. And 144. 144 is the 12th term of Fibonacci sequence. And this is f1 and equal to f2. So these are the only square terms in Fibonacci sequence. So from here one can able to find all the terms of the from here one can these are the only solutions actually that I'm saying. Similar type of questions also asked for this question like this Fn equal to 2 into x square. So for here, this is like n equal to 0, 3, and from this can be handled from here because we have a very good relation on this Fibonacci sequence. What is that? So it says that the GCD of the greatest common divisor of Fn and Fm, Fn is the nth term and Fn is the mth term, equal to F GCD of n and m. That means, so this is the divisibility properties of Fibonacci sequence. So we can say that this nth term and m, what is the GCD of nth term and mth term? That is something like the the terms where the GCD is the GCD of n and m is suppose d, then you can write this is fd. So here d equal to GCD of n and m. Okay, this is a very useful result. Using this result, some of these questions can be answered. So now, so the most important question, this is perfect square. Then people are trying to ask where Fn equal to x to the power q, where Fn equal to x to the power 4, or in general, when Fn equal to x to the power p. P is a prime number. Once we know prime numbers, then we can able to find the other numbers because we can factorize that numbers in that particular way. Okay. So the then finally questions we arrived at these questions. So what are the values of n where Fn takes the power values? Power values means it may be square, it may be third power, it may be fifth power like this. Okay. So after the proof of Fermat's last theorem, which was recently proved in 1994, then this question using the technique of this proof of Fermat's last theorem was solved. And this paper is published in the most reputed journal of mathematics, that is called Annals of Mathematics. That is in 2006. This is a very recent. This is a problem is very old, but the solution is very recent. So, and this was done by 4 mathematicians, 3 mathematicians: Bujo, Bujo, and Knott, and Siksha. So I mention this result because this result is looking very trivial because one can able to ask this question quickly, but the solution is very difficult, and that difficult question was answered after the proof of Fermat's last theorem using the techniques and tools. still they need several generalization of that tools. So using that tools, they have proved that these are the ones. So here the question is for what value of n, x, and p, this equation has a solution. So this nx and p belongs to this set actually. This is 1, 1, and p. If you take n equal to 1, then f1 equal to 1 and x equal to 1 and p is NP. And also if I take n equal to 2, then again f2 is 1. So this is f2, 1, and p. So this is the 6, 2, and 3. All these numbers we can see, just 2 and 2. So this is the set. That means this is all these are, so first 2 are 1, 1. So 1 equal to 1 to the power 3. And this one f6 equal to 8, that is equal to 2 to the power 3. And f12 equal to 12, so 144, that is equal to 12 square. So these are the all perfect powers in this Fibonacci sequence. Finally, this question was settled in 2006. What are the perfect powers in Fibonacci sequence? That these are the only perfect powers. There are no other terms. Any questions till now? Hello.
No, carry on.
Okay. So this is a online na, so I should know whether it is audible or not. Okay.
No, it is audible. It is going on perfectly.
So the next question is, we have discussed about the perfect powers in Fibonacci sequence. Let us discuss the binomial coefficient. So we know what are the binomial. This type of things are called binomial coefficient. This is n factorial by k factorial into n minus k factorial. So now again, this is a sequence. If I ask this question, fixing k, fn equal to, suppose my x choose 3. Okay. This is again the differential equation. So for what value of n and x, this equation has a solution. This is called the intersection of binomial coefficient with Fibonacci sequence. So I will just give this example. There are other things are there. So the solution of this question is nx belongs to nx equals to, we can say this is 1, 3. This is, if n equal to 1, we can choose x equal to 3. That is 3 choose 3 is 1, so n equal to 1. And the other one is 2 and 3. That is fn equal to f2 equal to 2. This is f1. This is f2 equal to 1. So this is again x equal to 3. So these are the only solutions for this equation. Okay. So this is one type of intersection of binomial coefficients and Fibonacci sequence. And the other question is. So before going to some other question, let us go to one problem of Herodotus. So that is Herodotus asked this question. So this is Herodotus, and when I can write this 2 to the power m equals to n1 factorial plus all nk factorial, where this n1 is strictly less than n2 is strictly less than nk. So for what value of m? So we need this m and n1 up to nk in integers. Okay. So for what value of m, n1, n2 up to nk, this equation 2 to the power m equal to n1 factorial plus n2 factorial up to nk factorial has a solution. And again, at the same paper, he has conjectured that 2 to the power 7 is the largest solution for this equation, that is 2 to the power 7 equal to 2 factorial plus 3 factorial plus 5 factorial. Okay. So this one can verify. This is 128, this is 120, and this is 3 plus 2 is 8. 3 factorial plus 2 factorial is 8. So this is 128. So this is the largest solution, and this solution is verified by another mathematician during that period, that is Lin. And he verified this conjecture and also asked the same question, for what value of m one can write 3 to the power m is n1 factorial plus up to nk factorial, and with the same condition on n1 to nk. And he shows that not only that, he also showed that the largest solution of this equation is 3 power 6 equals to 1 factorial plus 2 factorial plus 3 factorial plus 6 factorial. So why I am telling all these things here? So you can see this is also a sequence. If I ask the same question, when fn equal to n1 factorial plus n2 factorial, like this. So one can ask this question. This is again a differential equation where the nth term can be written as sum of factorials. Okay. So this question has a solution, that is only when k equal to, that is you can write f12 equal to 2 factorial square, this is 5 factorial, this is 120, and this is 4 factorial, this is 24. So this is 144, this is f12 is 144. This is the only solution of this equation. Fn equal to n1 factorial plus n2 factorial. Okay. So we have seen several differential equations when we intersect the sequence of Fibonacci numbers with the perfect powers, with the binomial coefficients, or with, you can see, what are the perfect factorial terms in the Fibonacci sequence. Okay. So now I will move to a smaller generalization of this sequence, because the title is S parts of perfect powers in recurrent sequences. We are just giving an example and discussing the perfect powers. Let us see what are the other generalization of this sequence, so that we can ask the same question about the perfect powers in other sequences. Okay. So the first generalization, which was called Lucas sequence. So this is Lucas is a mathematician. This is called Lucas sequence. So this sequence was defined like this. Let me take two integers p and q, which are positive integers, p and q. These are positive integers. And also we have assumed this condition, the series of p and q is 1. So greatest common, there is no common divisor. And also this p square plus 4q is not equal to 0. This is something like a discriminant. This will come in a minute. So a Lucas sequence is, with this assumptions, we can define Lucas sequence. So a Lucas sequence, I will denote the nth term of Lucas sequence by un, and since that there are two parameters, I will write like this: un p q is a binary recurrent sequence. Binary means this is order 2 recurrent sequence. Binary recurrent sequence that satisfies the recurrence relation. U0 equal to 0. The first initial, this is the initial terms. U1 equal to 1, and the relation UN equals to UN plus 1 equals to p times UN plus 2 times UN minus 1, where n is bigger than or equal to 1. Okay. So you can see, one can see this is the definition of Lucas sequence. So here we have two parameters here, p and q. So once we fix these parameters, then we can talk about recurrent sequence, Lucas sequence. So what are the parameters? If I take p equal to 1 and q equal to 1, we can quickly see that un plus 1 equal to un plus un minus 1, that is Fibonacci sequence. Okay. So you can also change to different parameters, to suppose p equal to 2 and q equal to something like -1, then we will get Pell sequence. So different sequence can be originated from this general definition of Lucas sequence. This is a Lucas sequence. This is a binary recurrent sequence. Just note that this is a binary recurrent sequence. This is a order 2 recurrent sequence with initial values 0 and 1. So in the next step, what we will do, we will again consider this binary recurrent sequence without any initial conditions. That initial conditions may be any random. Here we fix these initial conditions. So in this particular case, we are fixing our parameters p and q. But in the next, we are fixing our initial values 0 and 1. But when I will talk about binary recurrent sequence, at that time, we will not fix these initial values. Initial values can be any random, whatever we need, we can put that initial value there. Okay. So now the question is, in this case, you can again by the closed formula, we can again derive the closed formula, that is un equal to alpha to the power n minus beta to the power n by alpha minus beta, where this alpha and beta are roots of this equation. What are those roots? What are the polynomials? Polynomial is x square minus px minus q. This is called the characteristics polynomial of this Lucas sequence, and alpha and beta are the roots of this polynomial. So then I can say that this is the nth term un equal to alpha to the power n minus beta to the power n minus pi alpha minus beta. Again, one can ask the similar questions. For what values of n, un equal to y to the power p. Okay. Okay. So again, So when you can, one can also again this question for what values of n, y, and p, one can able to, this is Z3. Okay. So this is just we can ask these questions only for fixed p and q. Okay. So these questions can be later easily solved by a theorem, that is an important theorem in this Lucas sequence, that is called primitive divisors. So let me define what is a primitive divisor. So in the previous page, I have defined p square plus 4q is not equal to 0. That is been describing that I will denote like this delta equal to p square plus 4q, that is not equal to 0. So so this the integer p, which will not divide this delta, this is said to be a primitive divisor. This is a primitive divisor. If for the sequence un, if p divides un, but p does not divide un, where this m is strictly less than n. So now the question is whether such type of primitive divisor exist or not. So once you have defined something, so the next question is whether such type of divisor exists in Lucas sequence or not. So that question was answered by 3 mathematicians. That is also published in a great good journal, that's clearly in 2001. So this is called the existence of primitive divisor. So always in mathematics we ask two questions, whether they exist and whether it exists or that solution is unique or not. So the first question is the existence question here, existence of primitive divisors in this Lucas sequence. So this is proved by Billu, Harnott, and Bhautier in 2001. Okay. So they proved that for any n which is bigger than or equal to 30, the nth term of un of any Lucas sequence has a primitive divisor. That means once we have this result, that means this says that you always find a new prime. So once you get a new prime, then using that using this primitive existence theorem, existence of primitive divisor theorem, we can able to prove there are only finitely many solutions of this equation. Okay. So this is the development in recent development in this area. Okay. So now I will move to the more general question, that is the binary recurrent sequence. Then we'll go to the S units part. Okay. Is there any questions till now? Hello.
Carry on. If anybody wants to ask any questions, he will interrupt and ask. Okay.
Okay, so we have seen the first Fibonacci particular example of Fibonacci sequence. Then we have just extended Fibonacci sequence to Lucas sequence. Then the most general is binary recurrent sequence. That is, we have just the binary recurrent sequence is something like the order 2 binary recurrent sequence. So this is again given by un equal to p times un minus 1 plus q times un minus 1 un minus 2, where this p and q are co-prime and q is not equal to 0. If q equal to 0, this is not order 2 recurrent sequence relation. And u0 and u1. So I will not give any fixed value. So if I fixed u0 equal to 0 and u1 equal to 1, then this becomes a Lucas sequence. So this is with this any initial values, we can define binary recurrent sequence. And the important questions in this direction was asked by Petro, and this binary recurrent sequence is always given by C1 times alpha to the power n plus C2 times beta to the power n. So the C1 and C2 are roots of the characteristics polynomial x square minus px minus q. And the C1 and C2 can be determined once you able to give the initial conditions here. Okay, this is the closed formula for nth terms. So using this closed formula, one can ask this question: what are the values of n, x, and q? So there is some the echo is there. Is there any
Mahapatra sir. Mahapatra sir. Yeah. Thank you.
So again, one can ask the same question here: with what values of n, x, and q this equation is solvable? So since we can see that many things are not fixed here, p and q are random, u0, u1 are also random. So in this situation, this questions becomes more difficult. So finally, our Indian mathematician Sore and with a collaboration from Canadian mathematician Stewart proved that Sore and Stewart proved that in 1984 proved that this equation. So they have proved that this equation has finitely many solutions. This equation means this equation un equal to x to the power q. So they proved that the maximum of this n, x, and q is bounded by some constant c, and this c is effectively computable in the given parameters p, q, u0. Okay. So this was settled in 1984 by Sure and Stewart. Also independently by Petho. Petho is another mathematician from Hungary, and he also proved the same result, same result at the same time, and that are published in the same journal. So un equal to x to the power q has two solutions, two papers actually. So they prove that the maximum of n, x, and q is bounded by c. So once you have an upper bound, which you know, then we can see how in that range we can see what are the perfect powers. Okay, so this is the first part of my talk, that is perfect powers in Fibonacci sequence and Lucas sequence and in general binary recurrence sequence. So now what I will do, so we'll just a minute, we'll see what are the S units part in this recurrence sequence. For that, so we'll just ask this question like, let me define what is the S unit first. Okay, so for S unit part, I have to take a fixed set S equal to set of given prime numbers. This is given P1 to PS. This is given. These are all prime numbers. This is a set of prime numbers. Okay, then I will define a set ZS, Z subscript S. This is the set of all those integers which have no prime divisors outside the set S. No prime divisors outside the set S. Okay, suppose if I so let us give an example. If S equal to 2 and 3, then I can say my 2 square into 3 equal to 12. This is an S unit. This is because this is number which has the only prime divisors are coming from the set S. But if I take 5 is a number which is or I can take 5 into 7, that is 35. 35 is not a S unit because here S is 2 and 3. So it has two divisors 5 and 7, that is not from the set S. Okay, so now so we are calling this ZS, that is the set of all those integers which have no prime divisor outside set S, and the elements of that set are called S units. So if you can see, so this is P1 to the power A1. This is also an S unit because this has a prime factor P1. P1 is repeated A1 times. This is not an issue, but we are just asking for whether this is a prime divisor from the set S or not. So P1 to the power A1 is a prime divisor. Also, we can take P1 to the power A1 into P to the power A2. This is also a prime. This is also a S unit. So in general, if you ask me what are the general terms in this S unit, then we can write like this: P1 to the power A1 into P2 to the power A2 up to Pk to the power Ak, where these Ai's are integers, non-negative integers. Okay, maybe 0 or positive. Okay, so then this is called something like Wk, and this is belongs to the set Zs. Okay, so once we have defined this S units, then we can ask some questions related to Fibonacci sequence and S units. The first question was proved by, this is the first question. So let me write down the theorem. So let P be a fixed prime. So my S equal to P. Only one prime is there. Then question is for how I can write Fn equal to sum of S units. Sum of the S units means this is P to the power A plus P to the power B plus P to the power C. Okay. So here P is given to me. So I have to find N, A, B, and C. This is in Z4 or any positive integer. This is bigger than 0. Okay. So so this is solved only when A is bigger than B is bigger than C is bigger than equal to 0, and they have also proved this is answered by Petro and T. This is in 1993. And they have proved that this equation has finitely many solutions. That means they have proved that maximum of N, A, B, C is less than some constant C1. Okay, because C is already there. So with this assumption, they have proved this result. But this question is a little difficult than the previous question. If you ask P to the power, recall that this Fn is the nth form of Fibonacci sequence. So Fn equal to plus minus P to the power B, sum of two S units. So this is little difficult than the previous one, but with this condition, A and B, maximum of A and B is bigger than equal to 2. This has only finitely many solutions. It has only finitely many solutions. Okay. So these are the so we can give explicit solutions. For example, if I write the equation like Fn equal to power A plus 3 power B plus something 5 power C, here 2, 3, and 5 are 3 different pipes. So my A is equal to 2, 3, 5. And I ask this question for what value of N, A, B, C, Fn equal to 2 to the power A plus 3 to the power B plus 5 to the power C. With this condition is necessary. Otherwise, we cannot able to solve. Maximum of AB is less than equal to C. And this is maximum of AB is less than equal to C. Then on this N equal to, first N equal to 4 and ABC equal to 0. Because if A, B, C all are 0, then you will get 3 in the right hand side and F4 equal to 3. Okay, it's the first one. And if I write N equal to 6, then all this is 2. This is A equal to 1, B equal to 0, and C equal to 1. This is the solution of this question. Okay, this is now generally whatever we are theoretically saying, this is just 3 numbers. Then let us generalize this question again. So for this, this is a recent result by this is a 2017 result by Haidu and his collaborators. So this result is this is talking 2017. This is UN is any binary recurrence sequence. Here P1 and P2 up to PS are fixed given primes. So P1 is less than equal to P2, up to less than equal to PS are given primes. Okay, and B1 to BS are fixed integers, non-zero integers. Then the equation UN equal to B1, P1 to the power A1 up plus B2, P to the power A2 up to BS, PS to the power AS. So they have answered these questions. This maximum of this is less than equal to some constant C, and this is effectively computable. This one is effectively computable. Effectively computable means we can able to find this value once we give the given parameters B1, B2, BS, P1, P2, PS, and the recurrence, binary recurrence sequence means the initial condition should be there. Okay. So this is the recent development in this direction. So what I did in last 2, 3, 4 years, I have totally generalized these questions to a more general question and as follows. So we have considered a general recurrence sequence rather than a binary recurrence sequence. So a general recurrence sequence is given in this form: UN equal to A1, UN minus 1 plus A2, UN minus 2 up to AR, UN minus R, and this R is bigger than equal to 2. Okay, and this AR is not equal to 0. Otherwise, the sequence is not of order R. This is a recurrent sequence of order R. So because we have R number of initial values here, U0, U1 up to UR minus 1. Using these initial values, U0, U1 up to UR minus 1 and this recurrence relation, we can define the nth term of a, this is called the linear recurrence sequence of order R. This is called the linear recurrence sequence of how much time I have? Hello? Hello? Hello?
Yes.
How much time I have?
Actually, you are supposed to finish at 12:30 because of some problem. You can take another 10 minutes. You can wind up.
Okay. Okay. So let me conclude my talk with this few of my results. So this is called a linear recurrence sequence of order R. Okay. So that is you can see that this nth term is given by the previous R minus previous. We are using the previous R terms to find the next terms. Again, we need a closed formula. That closed formula again you can use the formal power series again generating functions doing all these calculations. We can able to find a closed formula. So for this closed formula, we have to write a characteristics polynomial. That is, this characteristics polynomial is x to the power r minus a1 x to the power r minus 1 minus minus ar. And this polynomial, suppose this polynomial has this is a polynomial of degree r. So let me write this is the product of alpha I to the power m mi. So this alpha is the root of this polynomial with multiplicity mi, and I is varies from 1 to t. So you can see m1 to mt is r. So this alpha 1 to alpha t are the roots, and the m1 to mt are the positive integers, which are the multiplicity. Then using these roots, we can write the closed formula un equal to f1 n alpha 1 to the power n f2 n alpha 2 to the power n up to ft n alpha t to the power n. This is the closed formula. This f1 n, this is a polynomial of degree m1 minus 1, and f2n, this is a polynomial with integer coefficients, and the degree is m2 minus less than m2 minus 1, like this. So this can be evaluated using the initial values. Okay. So this is a closed formula. Using this closed formula, we will prove our main result. So for that main result, we will also assume some of the technical terms. For example, when this un becomes 0, so that if in between there is 0, then the questions will be invalid. So what I will do, so first we have to consider such a sequence where there is no 0 terms in between. So for that, so what I will do, so we will consider the sequence should be non-degenerate. So let me define what is a degenerate recurrence sequence. So this sequence is called degenerate. This is called degenerate. If degenerate recurrence sequence, if there are integers I and j, if there are integers I and j with 1 is less than equal to I less than equal to t, so that this alpha I by alpha j is a root of unity. So what I will do in the next part, the sequence which is not degenerate is called degenerate. So otherwise it is called a non-degenerate sequence. Okay. So now my question is as follows. So I will consider this question. If you recall, my un equal to w1 plus w2 up to wk, where this wi belongs to the set zs. Zs is the set of s units. Means any random number. So if I write like this, any wi is something like p. If s equal to p1 to ps, these are fixed times, then this is something p i1 to the power e i1 up to p is to the power EIS. Any integer, any number, any units is of this form that we have seen already. So now question is for so we are writing any. So this is the generalization of all the questions we have discussed so far. So this includes sum of S units and Fibonacci sequence, Lucas sequence, binary recurrence, all these things. Because this is in the left hand side we have taken the binary recurrence. This is a sequence of order R, and in the right hand side we have taken the sum of S units. Means this if we take S equal to only 1, then I can write UN equal to some P1 to the power some E1 plus P to the power E2, something like this. So this is the whole generalization. And what we have proved, and this is published in, this is a recent result of mine. So this is in a joint work with Bursis, and this is joint work with Bursis, Haidu, and Pink. When I visited Hungary, there I have done this work, and this is published in 2019. This is in Journal of Number Theory. So we have proved that this is, so let me write down the theorem, and this is my final slide. So let UN be a non-degenerate recurrent sequence of order R, and Fx is the characteristics polynomial that we have seen in the last slide. Suppose that at least one of the following two conditions is valid. One of the two conditions is valid. That is, Fx has at least one irrational root. At least one irrational root. And second, f of 0 has a prime divisor outside the set S. Has a prime divisor outside the S. Then, for any fixed k bigger than equals to 1, this equation UN equals to W1 to WK is solvable at most for finite union. So this is the theorem. Here we have assumed that at least on one of these two conditions is valid. These two conditions are necessary conditions because if I assume that Fx has no irrational root, then I can able to find a counter example where we have infinite given solution. And also if I assume that f of 0 has a prime has no prime divisor outside S, then also we can able to produce an example where we have infinite given solutions. That's why we have restricted with these two conditions that at least one of the two conditions should valid. Either f of x has a one irrational root or f of 0 has a prime divisor outside the set S. Okay, so this proof is done using something called polynomial exponential equation. Using polynomial, there is a theory of again polynomial exponential equation. Polynomial exponential equation means this is a polynomial, but the exponents are variable. The coefficients are polynomial and the exponents are variable, and there are finite limit terms. This is not infinite series. Using the theory of polynomial exponential equations, we have proved this result, and this result is ineffective, and we cannot able to find what are those finitely many solutions. But in the next theorem, we have proved an effective version, but there is a more conditional. Generally, in such type of question, when you find explicit solution or any effective solution, in that case, we have to put some more conditions so that we can able to reach to our list. We can able to say that this is the constancy and the maximum solution will be always less than that C. So with this, I conclude my talk. Thank you.
Is there any questions from the audience?
Anybody wants to ask any questions can ask. Doctor, when we are studying that S units, right?
Yes.
And we know that every number can be expressed uniquely as a product of some prime numbers,
Yes.
So if that is the case, then what is the necessity of reading these S units? Because in your talk, what I understand, you have taken a Fibonacci sequence and you have taken the intersection of a Fibonacci sequence with some other Lucas sequence and combinatorics and all these things. So my question is, whenever you are taking an intersection with S units, then what is the necessity, what is the benefit of doing those things? Because we know that every number can be expressed as a product of some prime factorization.
Yes. So that you are
Hmm.
saying, you are saying the answer is because that is the fundamental theorem of arithmetic. So once we know the answers about the primes, then we can use that fundamental theorem of arithmetic to find the answer for any natural number. Right.
And
That
okay, what is most interesting about these number theories? Most of the problems are taken as conjectures, right?
the things are very
Uh,
easy to describe, but the proofs are difficult.
Very, very difficult, isn't it? Because we say that a perfect number is always even, but nobody has proved that it is odd. All these things.
ঘরে পুরো টেবিল আছে বড় বড় ওগুলো যে প্যাকেটে ধরবো প্লাস মাইনাস সব এনজি পার্ট
Dr. Abhijit, please switch off your microphone. Okay, Doctor, it's a nice talk. We'll have
Okay.
some other day. Okay. Any other fellow can ask questions? Okay, Dr. Abhijit,
Yes,
over to you.
Sir.
yeah. So at the end
Hello,
of
sir. I have a doubt.
yes.
Sir, you mentioned a formula that 3 power m is equal to n1 factorial up to factorial
Yes.
and fix m equal to 6 and found that 3 power is equal to 1 factorial plus 2 factorial plus 3 factorial plus 6 factorial. Then my query is, what is the characteristics of n1 and n1 up to nk here to find out 3 power 6, and how can I find out other powers of 3 using this formula?
No, other powers of 3 you can. So question is whether you can write 3 power m equal to n to the power n1 factorial plus n2 factorial up to nk factorial, right? Whether means we are asking for what value of m, n1, n2 up to nk such that 3 to the power m equal to n1 factorial plus n2 factorial up to nk factorial. Okay. And what I am saying is Lin proved that 3 to the power 6 equal to 1 factorial plus 2 factorial plus 3 factorial plus 6 factorial is the maximum solution. Maximum solution means you cannot able to find m bigger than 6 such that this is solvable. You can now, since you have 6 is a small integer, you can try for 3 to the power 1 and just try to write whether this is sum of some factorials or not. So what I am describing is 6 is the maximum power in 3, where you can write 3 to the power m as sum of factorials. And you cannot, beyond that, you cannot find. That he has proved.
Okay, sir. Thank
you. But from 0 to 6, you can try on your own. Like 3 to the power 3 is 27, you can write as 4 factorial is 24, plus 2 factorial is 4, 28, plus 1. So 1 factorial plus 2 factorial plus 4 factorial is 3 to the power 3. There are other solutions in between 0, 1 to 6. You can try yourself. There are very small numbers now you can do.
Okay, sir. Thank you.
Okay.
Anyone else would like to ask any questions? Anyone else want to ask question? Okay. If there are no more questions, let me express my vote of thanks on this 10th Siksha Anusandhan weekly academic lecture. We thank the speaker Dr. Sudhansu Sekhar Rout, whose talk has surely enriched our knowledge on linear recurrent sequences. Our thanks to due to colleagues, research scholars, and students in the audience. And big thanks goes to Dr. Manoj Ranjan Nayak, the Honorable President of Siksha Anusandhan University, who have been always been an inspiration for all of us. I extend our thanks to Professor Manjula Das, head of the Department Center for Applied Mathematics and Computing, and Professor Sunita Chand, the acting HOD, for the necessary supports and chairing the webinar, and Dr. Rudra Narayan Pradhan for connecting with Dr. Rout. Lastly, I, on behalf of the Center for Applied Mathematics and Computing, Siksha Anusandhan University, I extend our heartfelt thanks to all. So thank you all of us, and especially thanks to Dr. Rout for presenting such a wonderful talk.
Thank you.
Thank you once again, and thanks to all colleagues, research scholars, and students. So I'm officially ending the recording as well as ending the meeting.